Now we're going to be shifting here to shear design and beam. So first, we need to look at standard mode of failure. So shear is a force, is a strength. You need to have demand and capacity. Capacity is going to be called the strength, and demand is going to be like the shear force that you obtain out of the shear force diagram. So we have here two items. The first one is to find out the demand on the beam. Second item to find out the strength, determine the strength of the beam. I'm expecting if the beam is going to be kind of short beam and heavily loaded, I'm expecting that the shear is going to be controlling your design, which means the concrete section size is going to be based off the shear design analysis that you're going to be doing. If the beam has a long span and also it has some loads on it, I'm expecting that the flexure design is going to be controlling your section dimensions and the reinforcing in the beam. So first, to understand how to design for shear, you need to understand what is the expected mode of failure in shear. So let me remind you here with the expected mode of failure when it comes to flexure and beams exposed to moment, high moment demand. And I guess went through this before through a short video. And we have seen what's going to happen in a beam when it's going to be loaded with these 2-point loads. Reason that we have these 2-point loads usually in a shear or a beam design and testing is to be sure that the middle section is going to be exposed to pure moment and no shear force is going to be acting between these 2 points. So you split here the effect of shear versus flexure when it comes to beam testing. So what happened in this beam, we applied the 2-point loads, and as you see here, the flexure cracks is going to be right, the bottom is going to be going vertically. So all of this is what you call here shear, flexure cracks. So flexure cracks is due to the high bending moment in the middle, and you see here at the midpoint, the rebars at the bottom will snap, and you're unable to resist the maximum applied moment on this beam. So this area here it has a maximum moment, and we expect that the flexure or moment failure is going to happen right in the middle of the beam. How about the shear? You can say, okay, here's another beam, and here's going to be the flexure cracks, is going to be this vertical cracks. To a certain point now, if you look here at this crack is not really a vertical crack and is not happening at the point of maximum moment. Now let's look here at the applied moment. You have here 1-point load. When you have 1-point load, maximum moment is going to be right in the middle of the span. So here you have the point of maximum moment. Now this crack was initiated at this point here was maybe an angle of 45 degrees. If you try to measure this here, it's about maybe 45 degrees, somewhere in there, close to 45 degrees. So this crack is completely different from this crack. This crack happens because you have high tensile force right at this location. So if you want to look here at the type of forces right in the middle, they're going to say right in the middle, we're going to have high tensile forces. And this high tensile forces is going to start to create this crack, cause this crack right in the middle. But the crack that you're looking here at is completely different, doesn't happen at the point of maximum moment. Now someone's going to say, where's the point of maximum moment? I'm going to say, here's the moment diagram, your datum, and this is going to be your moment diagram. And here is going to be equal to 0, and in the top is going to be maximum positive, right? If you recall this issue of maximum positive, and here is going to be also equal to 0. And at the support is going to be equal to 0. So maximum positive moment happened in the middle of the span, and any cracks is going to happen in the middle is going to happen because of high tensile forces. Once you stay away here from the middle of the span, the flexure stress is going to reduce and you're going to have less cracks. You see this flexure cracks get reduced. But this big crack here is not really due to flexure. This crack is due to shear. I can show you another crack, but this is not in a test facility here. This is an actual structure. And look what happened. This is what you call here the shear cracks. And look, this gives you the support. We have here reinforced concrete wall. Here's the beam. and the crack is not really in the middle, the crack happens at the side of the beam. And you understand, if I go back here one step, if you want to draw here the shear diagram in a case like this, shear diagram is going to be this, going to be your datum, and then the shear is going to look this way. It's going to be your shear diagram. So the shear is going to be the same throughout the length of the beam, but most likely it's going to happen right here at the end of the support, because beside this point load, you have also uniform load that acts on the top of the beam, which is a weight. So I'm expecting shear cracks is going to happen at the end, flexure crack is going to happen right in the middle. So, okay. Let's look here at type of cracks. Is there a question?
Yeah, sorry, could you go back to the previous slide?
This one.
So
This one.
oh no, the next one. So we see some wooden crates on the bottom. Is that creating a middle support? And then we see this black bar.
Oh,
Is
this one
that
here?
loading at all?
Oh, this one here?
Yes.
This is applied point load.
This is
So what happens? You have a base plate.
Uh-huh.
Maybe you need to turn off the mic if you're not speaking.
Maybe you need to turn off the mic if you're not.
The echo. Okay. This is a base plate. And this is gonna be a jack. And then you have, this is like an old thread. They call this duodenum bar. And this here is attached to the floor. So it's not really a support. What happened? They're gonna be jacking the oil. And this rod wants to move up. When it moves up, this jack starts to push down. And with that, you apply the point load on the top of the beam. So this is like the mechanism to apply the load. It's a little bit different from the standard point load that you may look at. So it is not really a support. It just, it's not a support as a beam. It is a mechanism to apply the load on top of the beam. So this jack here, it wants to pull this rebar up. While it is pulling it up, this jack itself is pushing down on the beam. Does this make sense or no?
Yes, thank you.
Okay, no problem. So I'm going to be looking at one of the standard beams. I'd like to distinguish between cracks due to flexure and the cracks due to shear. You see here, you start to load the beam, and then all of these cracks, this is going to be all flexure cracks, which is right in the middle, right? And then all of a sudden, some other cracks is going to start to show. And they call this diagonal tension cracks or shear cracks, which is given an angle. And as you see here, this angle is about 45 degrees. Now, when you do a test, let's say that you're trying here to do a test, right? If I want to test this beam in shear, I need to make it really strong when it comes to flexure, which means I'm going to be providing here lots of reinforcing bars. So the beam in this case is going to be able to resist high moments without failing in moment or in flexure. And with that, at certain point, is going to fail in shear, because now you make the beam here is really strong when it comes to flexure. If you want to test this beam when it comes to flexure, so you want to test it for the moment or in flexure, you need to make it extremely strong in shear, so that's going to fail first in bending or in flexure. How do you do this? You make the concrete strong, and then you start to add here ties and other stuff that we're going to be discussing. But bottom line is, you want to test the beam in moment or in flexure, you need to make it strong in shear, right? If you want to test the shear strength of the beam, so you need to make it strong when it comes to the moment capacity. Otherwise, it's going to fail first in the moment capacity, and you're going to be seeing the shear damage or the shear failure. Like in this case, this beam is really strong in shear strength. And then you're testing it here, and then all of a sudden it fails in flexure. If it is not really strong in shear, it would have been failing in shear before flexure. But since we wanted to test flexure, you better make it strong in shear. Otherwise, it will fail in shear before it fails in flexure. Does it make sense? Yeah? No? All right. So what happened here? Before I start to do my test, I need to design the beam. I know if I'm going to be testing it for flexure, I need to make it strong in shear. If I'd like to test it in shear, I need to make it really strong in flexure. I'm going to show you here beam failure. We have seen this before, and that was the flexure testing. You guys see my screen? The testing? Yes? No?
Yeah.
All right. We are applying the 2-point loads at the same time. This section between the 2-point loads is going to be exposed to pure moment, no shear. And look at the flexure cracks right in the middle because you apply high tensile forces in the horizontal direction. You're going to see here no shear cracks at all, no shear failure because it is designed to be really strong in shear. And then at certain point, you're going to have more deflection, now it's going to fail. So, okay. How about in shear? What's going to happen? Let's say, look at the shear test. Here's the beam, you have 1-point load, and look how it fails. Now, my understanding is the crack direction is going to be perpendicular to the force direction. Meaning, when you have vertical crack, you're going to have horizontal force for the tension force. When you have a crack on an angle, I'm expecting also the force to be perpendicular to it, which means the force is going to be like in diagonal direction. Let's see some testing for some small beams in shear. Let's see what's going to happen. You see here, you may see some small cracks in flexure and some crack here. Now, this beam here is designed to be really strong when it comes to flexure. As you see here, we are going to be doing incremental load. And look at the crack. Look at this crack here. Crack means direction of the force, the tension is going to be in this direction here. You're going to have one force pulling this way, one force pulling the other direction. And look what happened. This is not flexure cracks. Flexure cracks is going to happen at the point of maximum moment. But look what's happening here. If you add more loads to it, more cracks. Crack is really getting large, right? This is going to be a big crack here. The beam is almost, I mean, now this beam technically it failed in shear. The bad thing about shear failure, when it happens to beams, you don't see loss of deflection. So beam doesn't deflect. There's no deformation, loss of deformation. It's sudden failure. So all of a sudden the beam is going to be collapsing. And you don't see the crack if you have a ceiling because you don't have lots of sagging. Look here at the amount of deflection before the beam fails. Look here at the deflection in this beam, almost no deflection. Look here at this deflection. I mean, look at the middle of the beam. The beam is almost straight. But just when the failure happens, the beam was unstable and collapsed down. So the bad thing about shear failure, they call it catastrophic failure. It is sudden. It doesn't show lots of warning. Flexure failure is ductile. It shows lots of warning before the beam collapses. Let's take here the beam. So here's our elevation of the beam. Let's take a stress element. We call this a stress element. If you guys remember Morse circle, so this is going to be a stress element. which is this stress element here. So we're going to take it out of here, put it right here. On this side of the beam, you have shear force going up. On the right side, you're going to have some shear force that goes down, right? So this is why when you look at the stress element, you're going to see that you're going to have some stresses going up from the left side because the shear force here is going to be positive, then it's going to be coming to be negative. For any stress element, if you take it, and then you start here to look at summation of the force in the x direction, summation of the force in the y direction, summation of the moment at any point is going to be equal to 0. This is to satisfy the equilibrium condition on this stress element. So when you look at this, look what happens. Summation of the force in the y direction is equal to 0. I understand that. So back to our discussion on the stress element. When you take here summation of the force in the y direction, the x direction, and summation of the moment at any point to be equal to 0, you'll end up by taking the moment about this point. You find out that you really need to have this conjugate shear component. And by doing this, in this spot, you see here that these two components will end up to a resultant is going to be in this direction, another resultant is going to be in this direction. This is what you call here the diagonal tension. This explains the direction here of the force to be in this direction, because actually in here, you're going to have one force coming this way, perpendicular to the vertical crack, another force coming this way, also perpendicular to the crack. But when it comes to this crack, you're going to have a component coming this way and a component coming that way. When you do the same thing on the other side of the beam, this is going to be the shear crack, and the two component forces, one of them is going to be coming that way and the other one is going to be coming this way. The stress element was taken from the left side. This is why the direction of the force is going to be in that way. Now we understand where this comes from. Why toward the end of the beam, you're going to have this component and this is going to be creating this diagonal shear crack. This is more analysis, little bit more detailed analysis of the force or the stress in the stress element. At the end, you're going to have two forces. It's going to be pulling this way, and this is going to be your crack direction. So the crack in the beam is going to be coming this way. And this is again for the stress element on this side. So I'm expecting when shear cracks is going to happen like this. And another shear crack is going to happen like this. Flexure crack is going to happen right in the middle. This is going to be all flexure cracks. This is going to be shear crack, and this is going to be flexure crack. Look at the crack direction. And most likely, this is going to be the direction of the force. And most likely, this is going to be at 45 degrees. And reinforced concrete beams is going to be most likely at close to be 45 degrees. So how can you resist it? The best way to resist this shear and to make the beam strong is to provide ties like this. And this ties needs to be contained about, or needs to go about, some longitudinal rebars. So I need to have here also some rebars on the top, right? And all of this ties needs to hook around it, and same thing in the other side of the top rebar. I need to have a couple of rebars on the top, a couple of rebars at the bottom. So what you're doing here, actually, you're providing ties to bring this beam together like this, as if you're stitching it. So you know the beam is going to be cracking like this. So you come earlier during construction and you just put the ties like this. So actually, if you like to resist the shear or increase the shear strength, what you need to do is to provide ties in the vertical direction. This is completely different from the horizontal bars that we put here at the bottom of the beam, so that we provide a strong beam when it comes to flexure or moment capacity. So I'm going to say, when you have here this at 45 degrees, let's say here's a crack, right? The crack is going to be like this. Now this beam, let's say it's going to collapse at a certain point. So if I may go back here to this previous slide, I'm going to say this means that this section of the beam, let me draw it this way. And here's the other section of the beam, which is in this section. So before you start to apply the load, this is like one beam. After you start to apply the load, what's going to happen? This section wants to go down, which makes sense. I mean, it's going to be feeling this way. Also, you can go back and look at the videos for the shear testing. Now let's look what happens here. You're going to say, here's my beam before testing. And let's say this give you the beam after testing. Now what's going to happen once you do the testing, shear failure is going to happen right at this surface. This piece is going to be coming down like this. So when you do the analysis here of this beam, you're going to say, here's the reaction. It's going to be right in the middle of the column. And then you're going to have some loading coming from the top. This load is going to be coming downwards. It's going to be like some uniform load like this. It's going to be coming downwards. Now I'm trying to figure out what is that force causing the shear, or where is this shear demand? How can I figure it out? You can say, if you want to take the entire force here, right, applied on the beam, divide this by 2 to give you the reaction and use the reaction to be your shear demand, I'm going to say this is not fair, because actually the shear failure starts to happen right here, and this piece is going to be going down like this, not with the entire force. It's going to be with a fraction of the force, which means this part of the force. Look, when this goes down here, this is going to be the force causing the failure. It is not really the entire force causing the failure. Meaning the critical section for shear is going to be right here at this location. And since we're talking about here 45 degrees, I'm going to be taking this out just for clarity. Since this is going to be at 45 degrees, a crack, they say here, look at the depth of the beam and go horizontally the same as this distance D. So if this is going to be D, look here from the face of support, right? This give you the face of support and go at 45 degrees to determine the critical section for shear. So actually V sub U, which is a shear demand, it doesn't necessarily need to be the reaction, but actually is going to be taken at D distance away from face of support. Meaning you need to look at here at the shear diagram. Let me try to do here the shear diagram. Let's say here's the shear diagram, right? Right, this gives you a shear diagram. And your disordered here at the support is called the reaction. So I can call it here R sub U. So R sub U is giving you the reaction of the column. And the shear demand that you need to design the beam for, it's not going to be this R sub U, and instead of it's going to be disordinate, which means this value here at the critical section for shear. And this gives you your V sub U. So I'm going to say here's V sub U. So V sub U is not going to be equal to the reaction. It's going to be a lower value. And why is that? You can see the reason is because this section of the beam is not going to be coming down when the shear failure is going to happen. Also, this part of the column here, no shear failure is going to happen in this block. So look at the column. You see this piece here of the column? This is going to be solid because this is actually supported right directly by the column. So no failure is going to happen here. You need to go at 45 degrees from face of support. So I'm going to say, where's the face of support? Is it going to be the face of this column or the face of this column right here? I'm going to say the face of this column right here, the small piece, the actual bearing. And you see here, this D distance is measured from the face of this bearing. You go D distance, and then you find out the shear demand. So the determination of the shear demand is going to be a D distance from face of support. Now, this is going to open the discussion for your current homework. The homework due. If you guys are able to open it now. Homework number 5. Here's your homework. it says here, determine the location of the critical section for shear and the design shear force. So to be able to answer this, you need to listen carefully to what is coming in a minute from now, which is this section here. All right, we're going to be working on those. So okay, good. So let's try to figure out location for shear section or critical section of shear. You guys see the slide set again? Yes? No?
Yeah.
Yeah.
Good. So when you have here continuous beam, in this case, V sub U, it can be on either side of the column. And again, you go here at 45 degrees on both sides, and then you can figure out V sub U on the beam. When you have a hanger, this is not a column. When you have a hanger like this, now think about the mode of failure. You think mode of failure is going to look like this? Would it ever happen? And the rest of the beam is going to be here on this side. Now think about it this way. If diagonal crack is going to happen like this beam will never fail that way, right? This will never happen because actually this works here as a ledge. This is like a support. So it will never happen like this. Critical section for shear in this case and shear mode of failure is going to happen like at the face of support like this. And this section of the beam is going to be just coming down like this. So in a case like this, the critical section for shear is going to be right at the face of support, not at the distance. Do you have another case? Yes. When there's a big point load that happens at the distance away from face of support, this is going to be the critical section for shear. Because this analogy that I was doing here at 45 degrees, it would not happen. Because you have here high concentrated load is going to be just breaking this piece here, this hunch or this ledge. It's going to be just taking it and go down. So in a case like this, critical section for shear is going to be at face of support. So for conventional beams or beams loaded with uniform load, critical section for shear is going to be at the distance away from face of support. And with that, you should be able to start to solve your homework with regards to this issue. All right, now the shear demand. How do you do the shear demand? Well, you need to have the load combinations that we went through before. Most likely, since we are going to be working with dead load on live load only, I'm going to be using this load factor or this load combination, and also this one. It's going to be 1.4 dead load versus 1.2 dead plus 1.6 live load. And then we'll see which one controls your design, which means which one is going to give you your higher force or shear force. Okay, shear strength is coming here from two components. It's coming from the concrete and the steel, the reinforcing bars. Now, which reinforcing bars? Is it the bottom reinforcing bars? I'm guessing no. Bottom reinforcing bars is for flexure, for a moment only. In this case, it's going to be the ties. If you remember, the ties is what is providing the shear strength for the beam, right? So I'm going to say I have here two components when it comes to strength. First component is going to be the concrete strength. Second component is going to be the shear strength coming from the reinforcing as ties. You just add the two values to each other. And of course, your answer is going to be in kips. This is not kip foot. Kip foot was good only for, if you recall here, kip foot for moment. Now we're talking about force, so it's going to be only in kips. Your phi factor for both components is going to be equal to 0.75. So it's good, we have it. There is no chart to find this out, or there is no change in the phi factor when it comes to shear. It's going to be only 0.75. The concrete strength when it comes to shear is so simple. It is given by this equation. Just one equation. You don't need the compression block depth. So actually design for shear is much simpler than design for flexure for a moment. Concrete strength without the phi factor is going to be equal to something that we call here shear factor. You see this number here, this constant, which is 2. We call this shear factor. Remember this call out or this name. This 2 is what we call here shear factor. The shear factor in this case is going to be equal to 2. 2 times what? Square root of f prime c. Now this is f prime c, it has to be in psi, right? Because we're in psi code, not ksi. So if you have 4,000, let's get, for example, 4,000 psi. Okay, we don't say 4 ksi in this case. BW is going to be the width of the web of the beam. So if you have a T section, you're going to be taking the web only. Slab is not contributing to the shear strength of the beam. And the depth is going to be the effective depth from the top compression to the tensile rebars. Equation is so simple. That's it. I mean, nothing more when it comes to concrete strength and shear. There is one limit here with square root of f prime c. It says this shall not exceed 100 psi, which means maximum f prime c to be used in this equation. The maximum is how much? 10,000 psi max. So f prime c itself is going to be max of 10,000. So when you do square root of it, it's going to be 100 psi. Just the limit. So okay, good. How about steel due to ties? When you add ties, right, you're going to have some strength coming to it. Let me show a picture here. Here's a picture of the ties. And the tie can be just one closed tie. We call this a closed tie. It can be combined with a few ties. For example, here's a U tie and a cat. In some cases, this is going to be easier to build. How about this one here? You see here, you can have 2 of this in the same time. So you're going to be repeating this at certain spacing. Let me show you what I mean here by certain spacing. I'm going to take you back here to one of the pictures. You see here the ties? The spacing between ties is what we call S. You see this S and S? And this S, let's say maybe 10 inch, maybe 12 inches, maybe 14 inch. And this give you the range. Maybe 8 inches, maybe 14 inch, somewhere in between, maybe 16 inch. But we usually try to keep it as 8 inches to 10 inches, maybe 12 inches. This can be appropriate for design. Okay. At each time here, you are going to have one tie or one stirrup. You can have also 2 in the same tie. Now, which component of this tie is giving you this resistance? I'm going to say, let me take you back here. Now, which component of the tie? Is the vertical leg or horizontal leg? I'm going to say, the crack is going to be kind of horizontal, right? I understand it goes here in an angle, but the vertical leg is what is keeping this beam together. Just to make this easy to understand, just imagine that you have this and you have it, let's say, made out of like any other material, not concrete. Something simple that you can crack by hand and then you can put it back together. So let's say a door. To bring this back together, maybe you can bring some rubber bands and just tie it, right? Just to bring it back together, to keep it in one place. It's exactly what you're doing, but instead you're doing it with the steel ties, because here you're talking about concrete. In a case like this, what's really bringing the strength is going to be the vertical leg. You see the vertical leg of the tie is what's causing the strength. As long as it is hooked around the top bars and the bottom bars. So now let me move forward and go to this picture of the ties and let's see what's going to happen. This tie here, in order for you to put it in the concrete, you need to have 4 rebars. You need to have a rebar here so that the beam itself or this tie itself is going to be hooking around this rebar. It's going to be a good tie because you have some longitudinal rebars top and bottom that this is hooked about. So when you have any vertical force on the tie itself, right? Vertical force means tension force. This rebar wants to go up like this. And then you have another rebar that wants to go down right? The bottom rebars wants to open up, and both of these two forces is going to be causing tension on this rebar. So this rebar now is going to be exposed to tension. Just imagine if you don't have this top rebar at this location, what's going to happen? Just going to slide, it's going to slip, because there's no horizontal rebar that this is going to be hooking around. So you really need to have a rebar at each corner of the system to be able to create the shear resistance. Same thing is going to be here. You need to have 4 bars, right? One at each corner. How about in this case? In this case here, I'm saying that I'm going to have 2 of these is going to touching each other. So in here, I'm going to have 2 ties of this tie A. They happen all together in one location. And they're going to be repeated at S distance. So at S distance, you're going to have a couple of these, right? So if I'm going to go back here, so you're going to have 2 ties here and 2 ties here, 2 ties here. Now, how many vertical legs do I have to resist the shear? In this case, I'm going to say I have rebars here that all of this tie is hooking about. So I'm going to say if I cut a section right here, right? How many rebars does I cut through? 1, 2, 3, 4 legs. So 4 legs of this tie is helping to increase the strength for the shear spread. If I'm gonna come here to this tie A, let's cut a section. How many ties? How many tie legs? I'm gonna say 1, 2. How about here? It's gonna be 1, 2. How about here? It's gonna be 4 of these. 1, 2, 3, 4. So the cross-section area that I'm working with is gonna be the vertical leg of the tie cross-sectional area. So now let me go back to my equation. Equation says Vs. What is Vs? Vs is going to be the shear component, right? The shear strength component. I'm going to take you back one slide. I'm done here with this Vc. Now I'd like to do this Vs, which is a shear strength developed by the steel ties. So, okay. Let me look at the equation. Vs equals A sub V. What is A sub V? I'm going to say this A sub V is going to be the cross-section area of the ties resisting the shear. Okay, not very clear, but I guess we can clarify. Fyt is going to be the yield strength for the ties. So this Yt is going to be yield strength for ties. So I understand this Fy, it could be different from the yield strength for the longitudinal rebars. This is why they call it Fyt, but it's just F sub y. How about the depth? I'm going to say, yeah, I understand that. This is what I've been working with. It's going to be distance from the compression to the tensor rebars. What is this S? I'm going to say S is going to be the spacing, and it is all listed here, tie spacing. So what is this S? Can I see it in the picture? I'm going to say yes. Let me go back here. This is going to be S, the spacing for the tie sets. How about this AV? I didn't resolve this AV yet. What does it mean by AV? Let's say, let's look here at this. Let's say that this here AB for number 3. So I'm going to say number 3 ties. How many legs did I cut through? I'm going to say 2 legs. I'm going to say 2 legs. How about AB for number 3 ties? Cross-section area for one rebar of number 3 ties, 0.11 square inch, right? When you have 2 legs, your A sub V, which means the shear cross-sectional area of ties, is going to be equal to 2 times 0.11 is going to be equal to 0.22 square inch. So in this case here, this is going to be the situation. You can have your number 3 ties, AB for 1 tie is going to be 0.11. I have 2 legs, your AV is going to be equal to 0.22 square inches. And this is actually AV that you're going to be using in your design here, in this equation. And S, of course, is going to be the spacing in inches. Okay. How about in a case like this? If I have number 4, so I'm going to change these values a little bit. Let's say here, I have number 4 ties. What is AB for number 4? Can someone help me? Yes?
0.22. Oh, no.
0.2 square inches. Okay. How many legs do you have?
4.
4 legs. I'm going to say 4 legs. Therefore, AV equals 4 times 0.2 is going to be equal to 0.8 square inches for A sub V that you should be able to use in your equation. All right. I have 4 legs. Each one of them it has cross-sectional area of 0.2. So I have total of 0.8 square inches. In this case, I have total of 0.22 because I have only 2. And we're talking about number 3 versus number 4. Are we good?
I have a
Question?
question in the previous formula.
This one.
Right. The yield strength should be the same as the Fy that we used before. So why is this Fyt?
Because you could have used, if you like, if you want to, in many cases, you can have used lower strength rebars for the ties. For example, you say Fy 40 KSI. So the only reason that you do it this way, just to give you a chance to use different bars for the ties if you want to. But if it's going to be also grade 60, you just use grade 60 of 60 KSI for the yield strength. That was very common in the past. So let's say you go back 30 years and you see here the ties are used of lower grade rebars. Not anymore, because this lower grade rebars doesn't exist. You cannot really buy it. You cannot find it. So everything is almost now grade 60. So in a case like this, your Fy for the ties is going to be grade 60. For the rebars, it's going to be grade 60. It's going to be 60,000 PSI. Now you got to be careful here. Which units would you use for Fyt? Are we using 60,000 or just 60?
Would we be using thousands?
You have 2 options here. If you like to use it in PSI, this is fine, but your VS is going to be in pounds. If you decide this to be in KSI, this is fine, but this is going to be in kips. So it's okay. I mean, this is not really tough, but this one is kind of tricky. You cannot really use 4 KSI. It has to be 4,000. So as long as you are careful, you should be able to use here PSI or KSI, as long as you know that if you use KSI, it's going to be in kips, use PSI, it's going to be in pounds. Okay, good. Let's say I was working on in a beam section and the shear was really in bad shape. I mean, the shear resistance was not good. So I started to add lots of reinforcing bars. The ties, I made it very closely spaced. I put number 4 at 3 inches spacing. I dumped lots of ties. You remember what happened when we added lots of rebars at the bottom of the beam for the flexure, right? We had a problem with this phi factor. The phi factor starts to drop down. And here we have a limit. They say this VS, you cannot just add any VS. Because if the beam is already a small section in cross-section area of the beam itself, if the depth is small and the width is very small, you cannot just dump lots of steel as on ties to make it very strong. You cannot, you have a limit. And your limit of this VS is going to be equal to 8 square root of F prime C. And of course, this is going to be in PSI. Let me put this here in PSI times B times D. I'm going to say, did I see an equation very similar to that before? I'm going to say, yes, it's right here. The strength of concrete is equal to a shear factor of 2 times square root of F prime C times the width times the depth. And the maximum steel is going to be 4 times larger than this. Look at this. This here 2. And what is the max for steel? It's going to be 8. At the end of the day, you add the concrete strength to the steel strength, will come to shear. Meaning that your maximum for any given section is going to be equal to 10 square root of F prime C. Where did they get this from? Well, we said concrete is going to be 2 square root of F prime C. And the steel tie is going to be 8. When you add them together, it's going to be a total of 10 square root of F prime C. That's it. Any questions? Okay.
I have a question about S.
Yes, absolutely.
It's not really, it doesn't make sense to me why that should be factored into its shear capacity.
This one here, you mean this limit?
No, not that one. To the left, how AV times FY times D divided by S. Why does that spacing matter in terms of shear strength?
Absolutely. What happened? Just a question, hypothetical here question, that I'm gonna come here to a beam. Let's say here's our beam, right? Exposed to shear and everything. I'm gonna come and put only one tie. Would just one tie make the job? I'm gonna put, let's say, number 4. Just one tie, number 4. You remember the length of this failure of this crack is how big? This looks to me maybe like 2 feet, isn't it? Maybe 18 inches at least. Look at this distance here. I'm gonna put only one tie here. Does it make sense to you? Would one tie do anything to you? You can see no. I need more than one tie to be able to gain good strength. So the spacing needs to be in there. When the spacing is gonna be small, it means that you put lots of ties. Right? Look what happened here in the equation. When the spacing here is small, the total strength here, Vs, is going to be going up. When this spacing here is equal, let's say 100 inches, this is going to give you nothing because you just put one piece of rebar. It's going to be very similar to the number of bars, if you like to compare it for the flexure design. Let's say for the flexure rebars, you put only 2 bars versus 4 or 6 bars. Would that make a difference in your flexure analysis and the mount capacity? I'm going to say yes. When you put more rebars, you're going to have more tension force. Of course, this is going to be to a limit. Same thing here to a limit. But if you just put one rebar, one tie, would that help? Just one tie and nothing else. I'm going to say, well, one tie is not going to be really keeping this beam together because the crack is going to happen, direction is going to change, the crack is going to be coming this way. So if I put one tie like this, the crack here is going to be going like this. Right? Because this tie is going to keep it in place. And the crack in this location is going to be going like this. So you're going to have 2 cracks here, and this piece here is going to stay in place. But failure is going to happen in shear. So you don't really have this full shear strength. If you want to increase it, you really need to come here, and then you're going to be adding a few ties. And the tie spacing here, this tie spacing should be more than 1/2 of the depth. Because if the crack is happening here on an angle, 45 degrees, let me take this out. Let me remove this one diagram and remove this and think about it in a good way. I'm gonna say, here's a crack, right? It goes on 45 degrees. There's no ties. The whole thing here is gonna be collapsing, right? So let me remove all of these ties. I'm gonna put here 2 ties. Here's one of them, and here's the second. So now where's the crack? Where's the crack is gonna happen? The crack is gonna happen like this. One crack is gonna start to happen like this, right? And the other crack is gonna be like this. The other crack is gonna be like this. Now we have the strength coming from this 2 vertical ties. And this crack needs to be at 45 degrees. So here I'm violating this rule. So actually it's gonna be going at 45 degrees like this, but guess what's gonna happen? It's gonna have this rebar in the middle. It's gonna be holding the beam together. If I keep the spacing here between the rebars to be equals to 1/2 of the depth, there is no way that this is gonna be at 45 degrees, right? It's gonna be like 30 something degrees. It's gonna be a ratio of 1 to 2, correct? So in a case like this, maybe 35 degrees or so. In a case like this, I can confirm that shear cracks will never happen unless the tie itself is gonna fail. Why? Because the shear crack wants to happen at 45 degrees. And with having this spacing between the ties to be equals to 1/2 of the beam depth, as a maximum spacing, now you are preventing the shear cracks. You are postponing it or you are pushing it. You're adding strength here to the beam and shear. So it is not just by one piece of rebar, one tie. You need to add a few ties here, right at this location, to be able to bring the beam together. Like in here, would you just add one tie? I'm gonna say no. You need to have a few ties to bring this together, because one tie means your AV is gonna be equal to only 2 bars, right? But once you have here the spacing, it means that you're gonna have more than one set of rebars applied here. Are we good about this equation?
Yes, that makes sense. Thank you.
Okay, thank you. So I'm gonna say here, the maximum strength of shear when it comes to beams is gonna be equal to 10 square root of MC. So 2 of them, the shear factor of 2 of this force is gonna be coming from the concrete. And maximum of 8 is gonna be coming from the steel. But also depends on the amount of ties that you put. But you cannot go beyond 8 or 4 times what the concrete is gonna be able to support. So here you're gonna say, okay, the concrete strength, let's say 100 kips. I'm just throw here some numbers. I'm gonna say, you know what? VC equals 100 kips. Let me do it in white. You can see here, VC, I did some analysis. VC equals 100 kips, okay? Just for sake of discussion. So good. How about the reinforcing bars? How much resistance would they have for shear when it comes to the ties? You can say this number in this case, this VS max is gonna be equal to how much? 400 kips. This is gonna be just the max, the limit. But the actual is gonna be based on the amount of steel that you put there, and let's say that you run the analysis, it is equal to 200 kips. Now, what is the total strength in shear for this beam? You're gonna say total strength is gonna be equal to 100 kips coming from this equation for the concrete, plus 200 kips coming from the steel. You're not gonna be using this 400 kips because it's just a limit. This is gonna be the cap. You cannot go beyond this limit. But of course, it depends on the amount of bars that you put in the beam. So I'm gonna say in a case like this, I'm gonna say this VN is gonna be equal to 100 plus 200 is gonna be equal to 300 kips in that case. And of course, PVC or PVN, if you like, PVN is gonna be equal to 0.75 times 300 kips at the end of the day. And how much is that? Can someone help?
$225.
For PVN. All right. Very good. So now I know the max when it comes to this. And then it says here, you don't really need to put any ties when you have a condition here. And we need to be very careful about this condition. This V sub U, when your demand is going to be very small compared to the capacity of the concrete. Because someone's going to say, I did here V sub U. I compare it with PVC only without adding any ties. I have a nice concrete beam. I checked the shear demand to the shear strength of the concrete only. Everything was great. Why should I add any steel, right? If the concrete or if the beam as a concrete only is very good and it has enough strength, why should I add any ties? So the answer is, you don't really need to add ties if your demand is lower than 1/2 of the concrete strength. So, okay, do we have minimum ties ratio that you can add or that you need to add to the steel beam? I'm gonna say yes. To the concrete beam, I'm gonna say yes. We have two equations. This is gonna be very similar to the minimum flexure reinforcing that they added there. I don't want to go through this now, otherwise it's gonna be too many equations, one shot. So now let's start and look at one equation, and whenever we need this minimum, we're gonna go back to it. Because I want to help you out to be able to solve your equation or to solve your homework. You need to finish your homework, right? So we need to finish this first. Give me a second, I want to open the homework this homework here, I need to do the location of the critical section for shear and the design shear force. So I want to concentrate on this design shear force before this time end of this lecture, you know. So we guys say, let's see this example. We have seen this beam section before. This is going to be the same beam that we have seen in previous examples when it comes to flexion. Beam width is 10 inches, total depth 16. I have 1.5 inch cover. I have number 3, number 8, number 4 ties at 14 inch. And guess what? This is going to be your S in your analysis in the spacing, right? And number 4 is going to be the tie. And your AV in this case is going to be equal to 0.4. Why 0.4? Because if you cut a section through here, you're cut through 2 rebars, right? So your AV is going to be equal to 2 times 0.2 is going to be 0.4 square inches. It says here in this example, determine the shear strength adequacy for the beam section shown below. The beam center line to center line span is 22 feet. So the beam span itself is 22 feet. Center to center, which means center of column to center of column. If you want to understand this more, I'm going to take you back to a previous slide. Say, where's the center to center? It means from this point to this point. From a support to a support. Also, if I may take you back to one of the previous slides, which is this one here. Just say it means from the center of this column. But our shear demand is measured at the distance from face of support. So my shear demand is going to be at the distance from face of support, which means it's going to be at the distance plus 1/2 of the column length. Where's the column length? This is going to be the column length, right? This distance from here to there. Support is going to be right in the middle. 1/2 of the column length plus the distance is going to get you to the critical section location. Now let's see what's going to happen in our equation here, our example. The clear span is 20 feet. So what's the clear span? The clear span is going to be from face of the column to face of column. So now we understand the clear span, which means from face of support to face of support, is going to be 20 feet. Your dead load given as 1.5 kip per linear foot. Now you don't need to include the weight or do any weight calculations. Live load is going to be 0.7 kip per linear foot. Okay, so I have the dead load on live load as a kip per linear foot. Concrete strength is 4,000 psi. The steel yield strength is going to be 60,000 psi. Great. The strength adequacy means find out the demand, find out the capacity, do the comparison. This is the meaning of it. Now let's work on the demand because you need it for your homework. Here's your dead load, here is your live load. You do the load combinations. You do the 1.4 dead versus 1.2 plus 1.6 live load. Here are the numbers. 1.4 times dead load of 1.5 versus 1.2 dead plus 1.6 live load. Now, which one controls? You can see this equation controls. This is going to be my design uniform load on the beam. So great. I guess I can repeat the steps here when it comes to my homework. Okay, now I have the load demand. Now I need to find out the shear demand. Now let me look here at the beam. The beam center to center span is 22 feet. Clear span is 20 feet. And this is very clear here, right? This is going to be the face of column. Look at this figure here. Here's the column. This is going to be right at the center of the support, right? And this is going to be the face of support. My D distance is 13.5 inch. How do I know it? I know it because I have the section properties, right? I have the depth 13.5. I'm going to go D distance away from face of support. You see here, this is going to be the clear span, 20 feet, right? You go 13.5 inch, and this is going to be your critical section of shear. meaning I need the shear value. And this give you my shear demand, and this is what you need to do in your homework. The actual solution of your homework is going to be in this couple of slides. 1, 2, and that's it. You just need to read this carefully, understand it, and just run the numbers same way. So uniform load in the top 2.92 kg per foot, which I got from here. I solved this first. Now I need to find out the shear at this location. Someone's gonna say, let me first find the reaction. I'm gonna say, fine, how much is the reaction? You take 2.92 times 22 feet divided by 2. I said, okay, this is fine. This is gonna be a reaction here. This is fine. This is a big reaction, the 32. But someone's gonna say, I can also find the shear here or some reaction here, which is gonna be based off this 20 feet. They say yes. If you take this 20 divided by 2 times 22.92 is gonna be 29.2. So this R sub U mentioned here is actually, this is not R sub A, this is gonna be R sub U, which means right at face of support. You see this value, which is the shear force. You see the shear force, 29.2 kips. Now, this is gonna be my shear diagram. And my understanding from the shear diagram, for each single foot that you move to the east direction, right? This is gonna be like the east direction for each foot. When you move east, your shear value is gonna drop down by 2.92 kip per foot. So okay, good. So what does it mean? How much is the shear right here at this point? I'm gonna say the shear right here is gonna be equal to the shear at this point, 29.2, and then it's gonna drop down by 2.92 for each single foot. This is the meaning of this. Load value 2.92 kip per foot. It means load is going to be going down by 2.92 kip per foot for each foot. So the shear demand at the critical section of shear is going to be equal to this 29.2, which means the shear at this section, subtracting this distance, 13.5 divided by 12, put it in feet, multiplied by the uniform load value. And with that, I have 25.92 kips. And this is going to be my shear demand. So I'm going to put here a box around this. With that, I'm done with my shear demand. Now, any questions? Finding out shear demand. I want you now, please open your homework and tell me if you have any questions. I don't want you to feel that this is not clear to you in your homework. And this homework number 5 is so critical for you guys. It is a very good training for your midterm, meaning that your midterm is going to have the same thing. It means it's going to be very similar to it. Of course, not in numbers, but ideas. Okay? So would you please open your homework number 5 and ask me questions if you have any? Here's the homework.
I have a quick question.
Yes.
So it doesn't mention anything from like face to face. Don't we need that to find like the actual length?
Let's address this issue. It says here center to center span of how much?
26 feet.
Okay, good. Do you have the column length? It says here that this length is how much? Center to center? This could be the center, right? So let's say here's the center, and here's the center. 26 feet. The column length is going to be 2 feet. So here's the column. Let me put here 2 columns. And each column is going to be equal to 2 feet. Distance from center to center is 26. And then you have a foot here and a foot here, which means the clearest span is how much? Your clearest span?
24.
24 feet. Very good. All right. Good question. Thanks, Peter, that you brought this up. Any other questions?
Does the question have to be like what we just learned right now, or can it be like from like question 3?
In here?
Yeah.
Oh, nothing here about the shear. But cracking moment, depth and compression block. This is when you have ignored the concrete flange effect, consider the compression reinforcement. You have done a beam with compression reinforcement, right?
Yeah, we've done them before. I just had a quick question on like number 3 when we're trying to solve for the depth. Because I was like playing the numbers and like it just didn't seem correct. So I wasn't sure if I was like doing it correctly.
Consider the concrete flange effect.
Yes.
This is gonna be like a T-beam. Give me a second, please. Give me a second. Yeah, I'm here. Yeah. What is the problem with item number 3? Problem 3. This is going to be ignoring compression reinforcement. This is going to be like a T section when you consider the effect of the flange, right?
Correct.
So actually, the beam is going to be simpler in analysis, and your A compression block depth is going to be very small. What compression block depth did you get?
Well, I didn't complete it because I was solving for A2
How
when
did
I was
you
doing
do
the whole thing.
it? Explain me, how did you do it?
So I separated the top, the flange and the web. So area 1 and area 2, right?
What was your A value when you do the analysis?
12 feet, about 12, I mean 12 inches, sorry.
12 inches for the A. How did you do that?
Yeah, that's what. So
Okay. How did you do it? Can you tell me the equation or what numbers?
so we used the 0.85 f of c prime.
What was F and C prime? F prime C.
3000 psi, but I converted that to ksi. So just
Okay.
3.
What was your AS value?
So I had 2 AS values.
2? Why?
Or
You
well,
have here 3
just
number
one.
9. You see my screen? It
Yeah.
says there's 3 number 9. So how much is AS?
That's just 3.
3 square inches?
Mhm.
Okay. And how about F sub Y?
The problem said it was grade 60, so 60 ksi.
Okay, 6 KSI. How about F prime C?
Now it was 3 ksi.
3 KSI. How about B, the width B that you use in your analysis?
18.
18 inch? When you do T section, it's gonna be 18 inch or 4 feet. When you do rectangular section and you ignore the flange, it's gonna be 18 inch. Now you don't ignore the flange, you take the effect of the flange. So your width is gonna be 4 feet, correct?
Correct.
So how much width?
So that's 48 inches.
48 inch. And you have a factor here. Okay, can you run the numbers and find out A, compression block depth?
Wait,
You
sorry,
remember what the equation says?
can you ask that again?
You know the equation, what does the equation say? Do you know?
Oh, the tension is equal to 0.85 times F of C prime times the area.
Yeah.
Uh,
And how much is the A compression block depth in this case?
Sorry, what was that?
How much is the compression block depth? A lowercase. How much value would you get for that?
Sorry, because I think I might have done this question incorrectly. I think I was confusing like part
Okay.
3 with
So
part.
how much is A now in terms of inches?
So I just plug in the values we just said right now.
Yeah, if you log in the values, what did you get for A? I just want to match my numbers.
Is A 1.96?
Well, I'm getting 1.47 inches.
Yeah, I got 1.47.
Okay. So, Peter, let's say it's gonna be 1.5 inch, right? So if it's gonna be 1.5 inch, it's gonna be less than 6 inches, right? For the flange thickness. So it's gonna work like rectangular section. You're not gonna have A1 and A2. So this is beautiful, right? And you wish your exam is gonna be like this. So you don't spend much time on it. You can just finish quick. Okay.
Yeah, okay. So we don't assume just because it's a T or looks like a
You need to
T.
solve first. You need to consider it to be first like rectangular section. Use 48 inches, which is a total width B of the flange. You run your analysis. You find out A compression block depth, and then you see if it's gonna be within the flange, it's gonna be a rectangular section. Deeper than the flange, it's gonna be a T section.
Okay, so and if it was more than 6 inches, that's when we do the 6 inches and then the A2, right?
Yes, this is correct.
Okay,
Absolutely.
got it. Okay, thank you.
No problem. No problem. Good questions, Peter. All right. Any other questions before we go? All right, guys. I'll see you next time.
Thank you.
Professor.
Thank you.